Questions from 4.1? Other than the typo with the G and the H thing, yeah.
That really threw me.
Okay. 36. Let's take a look at problem 36. Remember I said I'd do two problems here? So here's what 36 looks like. It's a quadratic function, so we've got f of x equals negative 3x squared plus 3x minus 2. And the instructions say graph each quadratic function. Now when it says graph it, you're going to have to label at least 3 points. And if it says find the intercepts, which we'll find out in just a second, we definitely want to label those as well. So it says graph it by determining whether the graph opens up or down, and by finding its vertex, axis of symmetry, x-intercepts, and y-intercept. Okay? So we basically need to figure out all that stuff. We don't have to find the domain and range. That's good. We don't have to state the max or min. That's good. We just need to do a really good job of graphing this. So if we look at this, what's the first thing we can tell by looking at it? Just at a glance, without doing any work, what can we tell? Okay, we know it's a parabola, right? And we know it opens down. Okay? What else can we tell by looking at it, not moving anything around? Okay, just looking at it, what else can we tell? Okay, we can tell it's been vertically stretched by a factor of 3. Everything's 3 times taller than it used to be. And the negative tells us that it opens down. Yes?
And it crosses at -2 on y-axis.
Very good. Okay, you can look at this, and in this form, you can just look at the number at the end. Whatever that constant is, that is the y-intercept. So we're going to write down that the y-intercept is 0, -2. If you put a 0 in for x, which is what you do to find the y-intercept, it's going to cross the y-axis at -2. So we know that much about it. Okay? Good there? Okay. I think the next best thing to do here is to find the x-intercepts, because this is already in a form where we can just start finding those. Because remember, to find the intercepts, plug in a 0 for x, that's going to find the y-intercept, that's this guy right here. And then we plug in a 0 for y, or same as f of x. So I'm going to put a 0 in here, and we're going to find that. So that's a quadratic. This is from 1010, so you should know how to do this. What's the easiest way to solve a quadratic? By factoring, right? So if this factors, we should be able to take 3, -3 and -2. Those multiply to be 6. Can we find numbers that multiply to be positive 6 that combine to be positive 3? Multiply to be positive 6, combine to be positive 3. Nope. You got 2 and 3, those make a 5 or a 1. You got 1 and a 6, those make 7 or a 5. Okay, so there's no way to make a 3. So this doesn't factor. If this doesn't factor, what do? Quadratic formula. Now, here's the nice thing about the quadratic formula, and this is why I advise doing problems like this way. You will most likely have one like this on the test. It's not going to factor. So here's what's nice about the quadratic formula. Part of the instructions here say find the vertex. Wasn't there a nice quick little formula that found the x-coordinate of the vertex? What was that formula? Negative b over 2a. Isn't there a negative b in the quadratic formula? And isn't there a 2a? So if you watch here, if you solve this using the quadratic formula, we can actually find the x-coordinate of the vertex as we're doing the x-intercepts. So this is going to be -3 plus or minus. I'm going to write 9. Is that okay? Minus 4 times a times c. Don't skip this step. That's going to be a -3, and that's going to be a -2. All over 2a, that's going to be -6. Is everybody okay with that? Okay, now remember the formula is -b plus or minus b squared minus 4ac all over 2a. I could take that and I could write it this way. -b over 2a plus or minus square root b squared minus 4ac all over 2a. See that stuff right there? That is the x-coordinate of the vertex. So we can look at this right now without doing any more work. The x-coordinate of the vertex is going to be -3 divided by -6. What's that? 1/2. We know the x-coordinate of the vertex is 1/2. Okay, so this is going to be 1/2, comma, figure out what that is in just a second. Okay, let's go ahead and finish this off. Am I going to be adding something to 9 or subtracting something from 9? I'm going to be subtracting. Right? So this is going to be minus, let's see, minus 24. Okay. So this is going to be negative 3 plus or minus the square root of, this is going to be negative 15 over negative 6. What happens when you have a negative underneath the radical? You get an I, you get an imaginary number. Can you graph imaginary numbers on the xy plane? Nope. So what this means is no x-intercepts. None. Doesn't cross at all. So we know it opens down. We know it crosses the y-axis at 0, negative 2. We know the x-coordinate of the vertex. How do we find the y-coordinate of the vertex? Plug it in. We're going to take 1/2 and we're going to plug it in right here. So this is going to be a bit of a mess, but we can do it. So we're finding f of 1/2. That's going to be negative 3 times 1/2 squared plus 3 times 1/2 minus 2. Okay, now we've got to work out the fractions and everything. Squaring fractions is pretty easy. What do? Square the top and square the bottom, right? So this is going to be negative 3 times 1/4. I'm going to make 3 a fraction by putting it over 1. This is 3 times 1/2. I'm going to make that a fraction by putting it over 1. And then this is minus 2. So here's what I've got. Negative 3/4 plus 3/2 minus 2. If I'm going to combine all of these, how do I do that? Get a common denominator. So the denominator I could use would be 4. So this is going to be negative 3/4. 6/4, multiply the top and bottom by 2. And this is going to be 8/4. 8/4 is the same as 2. So altogether I've got how many fourths? Remember, you don't change those to 12ths or something weird like that. I have negative 3 plus 6, that's going to be positive 3, minus 8, that's going to be negative 5/4. So this crosses the vertex is at 1/2 comma negative 5/4. So I'm going to take this piece of information, this stuff that I have right here, and let's graph it. So it crosses at negative 2. The vertex is at 1/2 negative 5/4. What's negative 5/4? 1 1/4, right? Okay, now, I ought to label a couple points, so let's definitely label that point right there. Let's label the vertex. That's 1/2 comma negative 5/4. This is a little more difficult than the ones you did in 10, aren't they? Okay. This one right here is at 0, negative 2. Okay, now let's stop and think about this for just a second. This parabola is going to open down. It's going to look like this. I said you ought to label 3 points. If we had x-intercepts, I'd have 2 more x-intercepts, so I'd have 4 points that I could be graphing here. Okay? And that would be nice. That would be very convincing to anybody grading your test or your homework that you know what you're doing. My question for you is, we don't have to plug in points to find another point because of this axis of symmetry. If I know where this one is, I know where that one is. How far is this point away from the axis of symmetry? 1/2. So if I'm at 1/2 here and I go another half, where would this be? This would be at 1, and I know the y-coordinate because it's level with the other one. So that's going to be 1, negative 2. Any questions there? Okay, that's the problem. If you can do that, you're in great shape. If you can't, you've got a little bit of work to do. I want to focus on this guy right here for just a second. We think that's on the graph, right? We think we got it right. Should we check? How can you check to see whether or not that point is actually on the graph? Plug it in. Let's see. So if we plug in a 1, we should get a negative 2. Let's come back up here. if I do f of 1, I better get a negative 2. So this is going to be negative 3 times 1 squared plus 3 times 1 minus 2. So this is going to be negative 3 plus 3 minus 2. Those will cancel each other off, and we get a negative 2. So when you plug in a 1, you get a negative 2. It's on the graph. Okay? All right. If you were a math nerd like me, you'd think that's kind of cool. Anybody think that's kind of cool? We just took a guess. Okay? We knew what the shape was, and we figured out, you know what? 1, negative 2's got to be on the graph, and it actually works in the equation. Isn't that right, Caitlin? Absolutely, right? Yeah. Okay. All right. Any questions there? All righty. Okay. When is that due? That is due on Monday. Okay. Okay. Part of what makes 1050 difficult is the speed at which things come at you. So you've got a whole bunch of information that comes at you really quickly. You've got to take your 1010 skills or your Algebra 2 skills and then add some more things on top of those. Sometimes those aren't too bad, but then you've got completely new ideas that are presented to you, and you've got a whole bunch of them, and you've got to keep track of them. One thing that helps keep track of them is recognizing patterns, and that's what we're going to do today. We're going to talk about polynomials, and we're going to introduce how we can graph all sorts of different polynomials. Okay? Really wild-looking shapes without a calculator, and just like we knew that 1, negative 2 was going to be on the graph, we could make a sketch of a really wild polynomial and know that, hey, that's what it's got to look like. Okay? I know where it crosses the axes. I know whether it touches or crosses here, how many times it wiggles around and stuff like that. Okay? So, it'll wiggle. Okay, so we're going to start off with some basic building blocks for polynomials. They're called power functions. Okay? So I've said this before numerous times. Every function makes a shape when you graph it. Okay? And once you know what that shape is, you can stretch it, you can shrink it, you can move it right, left, up, down, all that sort of stuff. One of the easiest type of functions to know what they look like are called power functions. Okay? So we're going to take these and we're going to do some transformations on those, and we're going to make polynomials out of these. Okay? So this is actually a type of power function. Now, when we did this before, I'm going to give you an example. We did things like this. F of x equals, let's say f of x equals 2. Okay? Now that is a power function. When we have a power function, it's like x to some power. So this would be like 2 times x to the what? How could we make that just a plain old 2? What exponent could we put on there? If I put a 1, then it's still an x. How can I make that turn into a 1?
0.
Very good. Okay. Put a 0 on there. Okay. So this is like a power function where the exponent is to the 0 power. Okay. So this is going to be just this line right here. Okay. This is another way of describing those parent graphs that we talked about earlier. It's a horizontal line. Okay? This is x to the first. Okay, we had a name for that before. What function did we call this? Okay, it is a linear function. It's called the identity, because whatever you plug in is exactly what you get out. So we get this shape right here, perfect 45. Okay? So x to the 0 is a horizontal line. X to the first is that perfect 45, that identity function. Okay, we know what this looks like. That's really familiar. So it's just a parabola. So we'll graph it. It'll look something like this. Okay, please put the arrows on each end because that emphasizes this does extend forever in both directions. It keeps going up and out. Keeps going up here and out, up here and out. Okay, x cubed, we also graphed that. Okay, that goes way up here, goes really fast in this direction right here. Okay, and then what happens on the left side? It goes down. Okay, and it should make it look the same here. So it looks about like this. Okay, Again, put arrows on the ends there. Now, if we had to find any similarities between these two and these two, this is to the first, this is to the third. Look at the shape. This is to the 0, this is to the second. Okay, look at the shape. Okay, we have some words that describe those. We'll come back to those in just a second. I just want you to watch those. Okay, everybody good with those two, or those four? Those are all just review, right? Okay, let me make this a little bit bigger. And let's take a look at these guys right here. Now, x to the fourth. When you plug in a 0, you get a 0. When you plug in a 1, you get a 1. What do you get when you plug in a 2? You get a what? You get a 16. So it gets big really fast. So it would be way up here. Okay, so we'd have a point way up there. And what about on the left side? Same thing, because it's going to be to the fourth power. If you plug in a negative 2, you get the same answer as if you plug in a positive 2. Okay, so that's going to be way up here. If you plug in a negative 1, you get a positive 1. Don't draw the rest of the graph yet. Okay, what happens if you plug in a 1/2? 1/2 to the fourth. Top's going to be a 1. Bottom's going to be a 16. It's going to be 1/16. So in between 0 and 1, it gets really small really fast. So if I draw this, it's steeper than a parabola. And in the middle, okay, right near 0, it comes down here really fast. It kind of levels off and goes like that. So this looks like a parabola, but it's not a parabola. It is much steeper, and a really distinguishing feature is in the middle where it bends, it gets really flat. Okay? Steeper and flatter in the middle. So it's not a parabola. Got it? Okay, let's take a look at x to the fifth. Plug in a 0, you get a 0. Plug in a 1, you get a 1, just like we do with all of these. Plug in a 2. Okay, well, it'd be 32, right? It would be way up here. So the point is it grows really fast. Okay? What do you think happens in between 0 and 1? Okay, it goes down here and kind of levels off. Okay? It's not a corner, but it kind of levels off. And then what about the left side? When you plug in a negative 1, you're going to get out a negative 1. So it's going to be kind of flat, and then it's going to go down really fast. So do you see some patterns? Do you see some similarities? Okay, what's going to happen with x to the sixth? Okay, it's going to go up on both sides. Okay, everybody watch please. I'm going to do this over and over again. With x to the sixth, it's going to start up here and it's going to end up here. And then in the middle, it's going to come down really fast. It's going to kind of have a quick bend to it, flatten off, and then go up. Okay? So it's going to look something like this. X to the seventh. Okay, I'm going to draw them this way. Everybody watch. I'm going to make it start down here. Let's see. Get it right. Start down here, end up here. Okay, that's what it's going to do. So it's going to grow really fast. It's going to level off, go through the origin, and then go like that. Okay. Again, arrows on the ends because it extends forever in both directions. Okay. So what could we say about all of these even exponents, these even power functions? Yeah, starts up here and ends up here. Okay, if it's an even power function, that's what happens. What if it's an odd one? Starts down here and ends up here. Okay, starts down and ends up. Okay. What name do we give functions that show this type of symmetry? These are even. And what are these? Odd. Can you see where the name came from? There are other functions other than power functions that show symmetry. Okay, but this is really where we get the names. Okay? All right, so let's take a look down here. Like I said before, once you know what the general shape is, you can stretch it, shrink it, move it right, left, up, down, and all that sort of stuff. So even though this is a new shape, and this is a new shape, we should be able to graph what it looks like. So what would negative 3x to the fourth look like? Okay, vertically stretched like this, right? It's going to open down. So this is going to go down here like this. What's that top point going to be? 0, 0. Okay? Normally we'd go over 1 and down 1 to the 4th. So we'd go down 1. We're going to go over 1 and down 3. We're going to go down 3. So this is going to be 1, comma, negative 3. Same thing on the other side. This would be negative 1, negative 3. Does that make sense? What about negative 2 x to the 5th? Do you know what x to the 5th looks like, and what would the negative 2 do to it? Okay, it would flip it across it would be a vertical flip. It's across the x-axis, actually. Okay, so it normally does this. It normally starts down here and ends up here. If we do a vertical flip, what does it do? Okay, instead of starting down here and ending up here, it's going to start up here and end down here. Okay, we won't worry about labeling a point there. How about this one? How about we write it the way we're used to seeing it? We'd usually see it written this way. Negative x to the 4th. You should know what that does. And then what kind of 1 is this? Plus 1. So this would take that and flip it upside down and move it up 1, because it's not in the parentheses. So it would look something like this. Okay, my question for you is that a parabola? Not a parabola. Kind of shaped like one, but a lot steeper and flatter in the middle. Okay? Okay, now here's the interesting one. Everybody in here, I could have, at the very beginning, before you even got any instruction, I could have said, hey, can you graph this? Okay? But let's think of it this way. That's the parent graph. What does the negative 2 do to the graph? Okay, it vertically stretches it. So it takes a graph that used to look like this, and it flips it. So it's going to look like this. Makes the points taller. So it's going to be steeper, like this. And what does the 1 do? Moves it up 1. So we should see a line that's been vertically flipped and made steeper. Looks like that. So crosses at 1, has a slope of negative 2. That matches with, take this graph, do a vertical flip with it, make it look like this, okay, and then make it steeper, and then slide it up 1. Okay, so you can even use these rules that we've been learning about to graph very simple things like that. It matches up perfectly with what you were taught in pre-algebra and algebra and stuff like that. Okay, are there any questions? All right, so those are the building blocks. Those are the easy ones. Those are called power functions. Okay, so we're going to talk about something called a power function of degree n. That sounds really scary, but it's a very simple thing to do. A power function of degree n looks like this. So if you haven't heard the word degree, degree just is the same as the exponent. So what's the degree of this power function right here? Degree 1. This one? Degree 3. Degree 4. Degree 2. It's whatever the exponent is. That is the degree of that power function. Okay? So this one is degree 9. By the way, degree 9, what would that look like? Start down and end up. So it's going to go something like this, right? Okay. All right, now let's talk about a new vocabulary word. So remember I said this kind of, you get some building blocks and then a bunch of stuff comes at you fast. You got to piece it all together. Okay, this is called end behavior. Okay, now what we've been describing here, this is the general behavior of even power functions and odd power functions. Even power functions start up here and end up here. Okay, the basic ones. Okay, and odd ones start down here and end up here. Okay, those are the basic shapes. So if we want to talk about end behavior, a polynomial of this form, look how ugly this looks. This is a fancy way of saying we're going to add a bunch of power functions together. Okay, it behaves like this guy right here. So all you have to do is look at the very leading term, look at the highest degree power, and say, well, this is generally what it looks like. Okay? So when we say for large values of x, what we mean is out near the ends. What we mean is toward negative infinity and toward positive infinity. Okay? So in the big picture, is it starting down here and ending up here? Or is it starting up here and ending up here? Maybe it's been vertically flipped, so it would start down here and end down here. Okay, does that make sense? Just talking in the big picture, what does it look like if you zoomed way out and looked at the ends? Okay? All right, so if we take a look at this example right here of the first term, the second, the third, or the fourth. So we've got 4 power functions that have been added together here. Which one determines most what it looks like? The very first one. So it will behave approximately like negative 3x to the fourth. So in the big picture, it's going to start down here, and it's going to end down here. That's roughly what it's going to look like. Now, Alex, you ready? Okay. Doesn't have to look like that. It might come up here, wiggle around a couple times, and then go down. Okay. And those wiggles are what we're going to spend a lot of time figuring out. Okay. Because the overall behavior, whether it starts down here and ends up here, that's pretty easy to figure out. Okay? Figuring out how many times it wiggles around and stuff like that, that's a little more important. Okay? So, if we take a look at this right here, what's the degree of this entire polynomial? Now, before you answer that, a lot of people look at this and say, well, he just said the degree of this would be the exponent, so that would be 4. This would be 2. This would be 1. And this would be 0, a degree 0 polynomial there. Okay? So a lot of people think, well, we probably ought to add it up for the whole thing. And that is not correct. Because what we want to think about is which one of these terms has the most influence on the behavior. In the big picture, roughly what does it look like? It looks like this one right here. So this is degree 4. Guess what this one is? This is degree 8. Okay? So you don't add up the exponents to find the degree of a polynomial. You just find the highest exponent because that's the one that determines the overall shape. It has the most influence on what it looks like. Does that make sense?
So is it always going to be the first one?
It won't always be the first one. Sometimes they'll write them in the wrong order. So that's a really good question. If you were in my 10-10 class, what did I say if they write things in the wrong order? Okay, put it in the right order because they're trying to trick you. They're trying to mess you up. Okay? All right. Now, just some, this is some vocabulary. I try to use this in my 10-10 class, so it's not a surprise here. The word 0 is just another word for X-intercept. So you could say 0, you could say X-intercept, you could say solution, okay? And occasionally you'll also hear the word root. You'll hear the word root of a polynomial. What we're talking about is the zeros, the X-intercepts, the solutions, and that sort of thing, okay? So a 0 of a polynomial is something that when you plug it in, you get a 0. That seems like a pretty logical name. If the y-coordinate is 0, if the function value is 0, where is it? Well, yeah, but 0 is the y-coordinate. Where are you if your y-coordinate is 0? You're on the x-axis. Very good. You didn't go up or down. You just went right or left. Okay? So that's why it's another way to describe what the x-intercepts are. Okay? If that function value is 0 there, okay, then that means x minus r is a factor. And it also means that r is an x-intercept. Now this looks like we're moving along pretty quickly. We've introduced this weird vocabulary. We've got this weird thing that says, well, if this is 0, then x minus r is a factor of the original function, and r is an x-intercept, and that sort of thing. Let me show you what we're talking about here. So if we have this polynomial, okay, and notice that this is already factored. It says find the zeros. In other words, find the x-intercepts of that polynomial and then graph the function. So let's just look at this. There are 4 factors. What's the 0 or the x-intercept that comes from the first one? The first one, very first one. 0. What's the one that comes from this one? 2. Negative 3. Careful. 5 halves. 5 halves. Okay? Everybody good with that? Does that make sense? Okay, now, If I were to go through, so I heard Kirsten over here saying, well, let's multiply these together. Watch what happens if I multiply these together. Remember, I'm interested in the overall behavior. Okay, what's the degree of this polynomial? If I multiply these two together, I'd have x squared. If I multiply it by that, I'd have x to the third. And if I multiply it by that, I'd have 2x to the fourth. Isn't that what I'd have as the leading term? Does that make sense? Now we could go to the trouble of multiplying these all together, but that's a bit of a pain in the butt. And do we really care about those terms on the end? Or do we care about that first one right here? That first one has the most effect on the shape, most influence on the shape. So it looks like 2x to the fourth. So that means it starts up here and ends up here. Let's find out how many times it wiggles around. So it's got to cross through 0. It's got to cross through 2. It's got to cross through -3, which is right here. And it also crosses through 2.5. So here's what happens. Ready? I know it crosses at those 4 places. I've got those marked. And I know it looks like 2x to the fourth. So does it start down here and go up? Or does it start up here and end up? Okay, so we're going to come down here. We're going to cross through here. Turn around and hit that one. Turn around and hit that one. And we got to make a quick turn around. And there we go. So it's got a couple wiggles in there, right? Okay, yeah. I took x times x, that's x squared, times x, that's x cubed, times 2x would be 2x to the fourth. Good question. Anything else? Does that make sense? Okay. All right. Let's take a look at this next part. Okay. A polynomial of degree n has at most n minus 1 turning points. Okay, so these are the wiggles that I was talking about here. So let's put a number to this. What degree is this polynomial? That's 4. This says whatever the degree is, you take the degree and you subtract 1. That's how many turning points it can have. So how many turning points can this one have?
3.
Okay, up to 3 turning points. So let's watch. Turns once, turns twice, turns 3 times. Now, it doesn't have to turn 3 times. It can turn up to 3 times. In fact, we can see a really simple example right here. There's x to the fourth. The degree is 4. How many turning points does this have? Just 1. It doesn't have to have 3. It doesn't have to have n minus 1 turning points. It can just have up to that. Okay? So let's practice this a little bit. This kind of puts it all together. What degree is this polynomial? 4. How many turning points can it have? Up to 3. In fact, let's put that. Up to 3. Okay, this one's a little harder. X squared times x squared. That'd be x to the fourth. Times another one, that would be x to the fifth. So the degree is 5. How many turning points can it have?
4.
Okay, so up to 4. Would you do the next one, please? The one we did up above, right? Up to 3. How about this one? Okay, 1. In fact, if it's x squared, it's got to have a turning point. Okay?
That's a parabola, right?
It's parabola. And what about x cubed? Okay, up to 2. Okay, now we know this one. Okay, let's take a look at that. It says up to 2. Does it ever turn around and start going down? Does it ever actually turn directions? No, so that actually has no turning points. Okay, an odd one has that option, an even one doesn't, because it's got to start up here and end up here. It had to turn around at least once. Okay, if it's an odd power function like this, it can just keep going up the whole time. Okay, so pretty wild graphs, but if we know the basics about parent functions and power functions and stuff like that. Makes it a lot easier. Okay, any questions? Okay. Let's see how far we can get in this. Go ahead and flip the page over. Okay, few more vocabulary words, and then we're going to be able to put all this together. Okay, this is what you're going to need to be able to practice over the weekend, and that we'll fine-tune on Monday. Okay, so it says this. It says if x minus r raised to the m is a factor of the polynomial. So if we've got that as a factor, so if we've got something like x minus 2 quantity to the third, okay, we already know what the x-intercept is, or the 0 that comes from this. It would be 2. But now we've got this extra word here. It says r is a 0 of multiplicity m. Now we're going to talk about what a big deal multiplicity is in just a second, but let's just practice this for a second. The 0 that comes from this, the root or the x-intercept, if you want to call it that comes from there, is 2. But it has a multiplicity. Because there are 3 of those factors, it's really x minus 2 times x minus 2 times x minus 2. Its multiplicity is 3. It's that simple. So you look at the factors and you have to figure out 2 things on each one of the factors. What's the 0 and what's its multiplicity? Okay? So what's the 0 that comes from this guy right here? 0. What's its multiplicity? Multiplicity is 4. Okay? For this next one, what's the 0 that comes from here? 1. What's its multiplicity? I hear a couple ones. You are correct, because remember, if there's nothing there, it's not a 0, it's a 1. So its multiplicity is 1. And then the last one, what's the 0? Negative 4. And what's its multiplicity? Multiplicity is 3. Okay? All right. Any questions? Okay, we're almost to the fun stuff. We're about done with the boring stuff. Yeah.
So then what is multiplicity?
I'm going to tell you right now. Okay? Ready? Okay, so here's the next theorem. It says if r is a 0 of odd multiplicity. So if its multiplicity is 1, 3, 5, 7, 19, 211. If it has an odd multiplicity, then the graph crosses the x-axis at that point. If a 0 is of even multiplicity, then it touches. So this has to do with the wiggles. Okay? This will help us figure out where it's turning and where it's not. Okay? So this says on this next example, can I slide this down? Okay. It says, find the multiplicity of each 0, then state whether the function touches or crosses the x-axis at that 0. Okay, so we're going to do this. Okay, what is the x-intercept, or the 0, or the solution that comes from there? Negative 2. What's its multiplicity? Multiplicity is 1. So what does it do? Crosses. Okay, that's the information from this guy right here. Next one. What's the 0? 3. What's its multiplicity? 2. Touch or cross? Touch. Okay. Has anybody seen this before? Okay. Some people, rather than say touch, they say bounce, or they'll say, I'm not a fan of this, but some people say it kisses the x-axis. Okay, we don't need any intimacy in the classroom, so we'll leave that one out. Okay, but some people use different words. Whatever works for you, that's fine. Okay, and this last one, what's the 0? Negative 5. What's the multiplicity? 3. Touch or cross? Cross. Okay. Yes. You are jumping ahead.
And it says identify the graph, and none of it says the.
We'll get there in just a second. Okay. All right. So we could graph something like this right now. We'll start off with some easy ones. So let's take a look at this right here. Now let's go ahead and do this. Okay, just watch. Don't write this down. Okay, I need this to go through -2. I need it to go through 3. And I need it to go through -5. Okay. If I multiply all these together, that's going to be x. That's going to be x squared, so I'm up to x to the third. And this is going to be another x to the third, so this is going to look like x to the sixth, right? So it's got to start up here, and it's got to end up here. What do I do when I get to -5? Cross. Okay. Find -2. What do I do when I get to -2? -2? That one's a cross. What do I do when I get to 3? Touch. Okay, or bounce off there. So it's going to come down here, it's going to touch it, and it's going to go like that. Okay. Now, does it start and end in the right place? It's x to the sixth. It should start up here and end up here. Did that work? Did it cross at -5? Yep. Cross at -2? Bounce off or touch +3? Yep. How many turning points does this have? 1, 2, 3. Okay, it can have up to how many? Up to 5. So are we within all that? Okay, so that's how we do that. Okay, let me erase this, and let's see if we can. Let's see if we can get 7 and 8 done. That would be really good if we could do that. So this one says graphing a polynomial using x-intercepts. So what's the x-intercept that comes from this first one? 0. What's its multiplicity? 2. So what does it do? Touches, because it's even. What's the x-intercept that comes from here? Okay, so that's going to be 2. What's its multiplicity? 1. Touch or cross? Cross. Is that good?
How do you tell whether it touches or crosses?
You look at the multiplicity. If it's the even multiplicity, it touches. If it's odd multiplicity, it crosses. Okay? And then we're also going to say this, looks like, okay? When I say what does it look like or what does it resemble, that's where we multiply the first terms together and we figure out, hey, this is x squared times x. It looks like x cubed. So that tells me I've got to start down here and I've got to end up here. So let's put these points down here. It's got to go through 0 and it's got to go through 2. Okay, so I'm going to start down here. I'm going to go up, and when I get to 0, what do I do? What does it say it does at 0? Touches. So we're going to touch here, okay, bounce off that way, and then I've got to go through this one right here, and that's what it would have to look like. Any questions there? Okay, find the x and y intercepts of the graph. By the way, if you plug in a 0, what do you get? You get a 0 here times -2. 0 times -2 is 0. That is the only place where it crosses the y-axis. It crosses right at the origin. Okay? Use the x-intercepts to find intervals on which the graph is above the x-axis and where it's below. Okay, so let's state that. It's above. Where's it above? Where's the only place it's above? From right here to infinity. So that's from 2 to infinity. Okay, and where is it below? Well, it's below here, and it's below here. So it's really from -infinity all the way up to 2. There's one place where it's right on the axis. Okay, whoops. As long as it's not equal to 0. Because right there, it's actually on the x-axis. Okay, any questions?
So if you were describing increasing and decreasing.
Well, you'd say it's increasing from -infinity to 0.
Oh, because it's just the x.
Okay. Yep. Got it? Okay, let's look at this. What would change if that had a negative in front of it? Would it change the 0? Would it change its multiplicity? It's still a 2, so its multiplicity would still be the same. Would it change that 0? Nope, and its multiplicity would still be 1. The only thing that would happen is it would look like, instead of x cubed, it would look like negative x cubed, which would mean it starts up here, bounces off here. It would just be a vertical flip of that graph, okay? All right, any questions? Okay, let's, we're good there? Okay, let's take a look at 8. Okay, identify the graph of the polynomial function. It says, which of the graphs in figure 18 could be the graph of this guy right here? Let's see. There's one we can throw out for sure. This has got to look like x to the 4th. What does x to the 4th look like? Where does it start? Starts up here and ends up here. Which one can we cross off? Cross off D. Okay. How many turning points? Up to 1 less than the degree, so up to 3. How many turning points does this one have? 1, 2, 3, 4, 5. Can't possibly be that one. Okay, these both start up and end up. 1, 2, 3. 1, 2, 3. Okay, we're good there. So, gosh, it looks like both of those could be it. Okay, and here's where one more important piece of information comes in. Do you remember how the last couple days I've been saying intercepts are really important, both x-intercepts and y-intercepts? What's the y-intercept? Y-intercept has got to be -6, so that rules out that one. It has to be this guy right here. Okay? Now, take just a second and think about all the stuff that we've covered here. That's a lot of information. Okay? But just with what we've talked about really for about a half hour is about all we've been talking about this. We can look at this graph, which looks ridiculously difficult, and we can say, you know what? It could look something like that. It's got to have a y-intercept here. It's got to start up here and end up here. Okay? I'd like you to try and do problem number 9. Okay? Take a look at that and get started on the homework. We'll finish this up on Monday. I'll give you some time to work on Monday. But remember, we're going to correct 4-1 on Monday as well. Have a great weekend.